Welcome back. So as promised, what we're going to do today is try to figure out how to minimize this measure of goodness of fit, the average vertical distance between every point and, in our case, a line with a slope and intercept. So let's review and then we'll dig into how exactly we're going to do that. Okay, so where do we leave off? Let's simplify things a little bit just to make this a little bit easier to do. So what I'm going to do now is assume my model is just m. So I'm going to assume that the intercept is 0. So every point yi is equal to some scalar value m, which of course is the slope of the line, times xi, and I'm going to leave off the intercept. And you're going to see why I'm going to do that. It's going to just simplify the derivation about least squares. We'll eventually go back and put in that intercept there. So let me remind you what we're going to do. We are going to compute the vertical distance between each point and the line. The line is now parameterized just by a single point. So let's first of all figure out what delta is for this model right here. Well, let's see. It's just going to be the vertical distance where the point is, that's y sub I, minus where it should be. Well, where it should be, it's at mxi. So this delta is now just mxi minus yi. So the difference here from before, the previous segment, was just I had a plus b over here. So this difference now is just mx minus y. Good. And remember that what we want to do now is take that delta, parameterized for each point, and sum up all those values for all points. So I have the summation from I equals 1 to n, there are n points, of m, that's what I'm trying to solve for, times the x component of the data point minus y component of the data point, and then the whole quantity square. Why did I square it? Well, remember, I don't care if the distance is positive or negative. I'm trying to minimize the deviation, and we had sort of two options, take the absolute value or take the square. You're going to see in a little bit why I chose to take the square, but there it is again. I chose the vertical distance, and I chose the square, and I chose, frankly, to sum them all up. I could have done something different and treat all the data points equally. And so our job now is to find the m, the model, that minimizes this error function. Yeah, sometimes called an objective function. All right, so how do we minimize this? So m is embedded in there, and well, we could do a sort of brute force search, right? I could say, okay, let m range from minus some big number to positive some big number in some small increment, and I can evaluate this error function for every single value of m, and then just take the m that minimizes it. And within whatever range that we're skipping over those m's, I'll have found the minimum. It's pretty clunky, right? I got to search a lot of values. It's not particularly efficient. It turns out it's not necessary. Let's see why not. Okay, so let me start by so what's the game? The game is we've got to get the m out of there, right? It's sort of like trying to solve an algebraic equation. We've got to get the m out of there. So let's start teasing apart this thing. Okay, so what do I have here? I have mx I minus yi quantity squared. Well, that's just mxi minus yi times mxi minus yi. Notice this whole thing is still within the summation, right? So it's this indexed on 1 plus this indexed on 2 plus this indexed on 3 plus and so on and so forth up until n. Okay, so I can factor that polynomial out. So let's go ahead and do that. I've got, okay, let's do the multiplication. I've got this term times this term. So it's m squared xi squared. And then I've got this term times this term. That's m xi yi. And then I've got another one right here. So this one's a negative. This one is a negative. So I've got minus 2m xi yi. And then, of course, I have a plus because it's a negative and a negative yi squared. Okay, so it looks like we're making a little bit of progress. I mean, it's not quite as gnarly as it is up here, but I've got an m squared term here and an m term here. And of course, it's all still embedded in this summation here. So let's see what we can do here. Well, let's see. I've got the summation out here, and I've got a term plus another term plus another term. Well, if I've got a summation and then I've got a sum of things, well, that's the same as summing the summation of them. So I can bring the summation into here and then bring the summation into here and bring the summation into here because it's all just a bunch of sums, and the orders in which I do them is completely irrelevant. So let's do this term right here and only that term. Well, notice that m, of course, is not indexed on I. The only thing that's indexed on I is, well, x sub I squared. So this term, ignore this thing here for now, if I did the sum from I equals 1 to n of m squared xi squared, well, what is that? Well, it's m squared times x1 squared plus m squared times x2 squared plus m squared times x3 squared up to xn squared. So notice I have a common m squared term, and then I've got the sum of the squares of the x components. Okay, good. That's nice and clean. Now I can deal with this component. So I've got same thing. The 2m is not indexed on I. So all I'm going to do is sum up all the xy pairs. So I've got x1, y1, x2, y2 up to xn, yn. And that whole quantity, which of course is just unraveling the summation, is going to be multiplied by 2m. And then lastly, I just have a sum of the yi squared terms, and there's no m in there, so that's just the sum of all the yi terms. Okay, so this is starting to look a little bit better, although there's a lot of terms here. Why is it looking better? Well, I've got an m squared term here, I've got an m term there, and I've got, well, just some other thing here. Now, again, what do I know, what do I not know? I don't know what the m is, that's what I'm trying to solve for. Well, what do I know? Well, I know all the x terms, I know all the y terms here and here, and so I could just evaluate this, yeah? And that's just some scalar value. So take all the x terms, square them, sum them. Take all the x and y terms, multiply them together, and sum them. Take all the y terms, square them, and sum them together. And let's just call that a, b, and c, right? Just some scalar value that you can evaluate for all your data points, okay? So once I do that, what does this thing up here reduce to? It reduces to a m squared plus bm plus c, where a is that term, b is that term, and c is that term. Wow, this is some good news. First of all, I got a polynomial. Polynomials are nice. We know how to manage those. And it's looking a lot more manageable. So when I tell you to find the m that minimizes this, it looks a little bit less complicated than the m that minimizes this. You got the m inside the square, and that whole thing is inside of a summation. But it turns out that this is actually a pretty simple expression. It's a polynomial. And in fact, what does a polynomial look like? Well, it's a parabola. Well, it may be an inverted parabola. We'll come back to that in a minute. So what is the axes here? Well, this is a parabola in M. Yeah? So A, B, and C dictate the shape of the parabola. So this axis is M, the horizontal axis. And this axis is what? Well, whatever this evaluates to for each given M. Well, why is that good for me? Well, what am I trying to do here? Well, let's go all the way back to where we started. I'm trying to find the m that minimizes this quantity. We just agreed that that quantity is this quantity, and we just agreed that that quantity is a parabola. So what is the m that minimizes this? Well, it's that value right there, where the parabola hits a minimum. That's what I'm looking for. And so remember when I said early on is, look, I could search for all the values of m. I can start from a really small value, a negative value of m, and go all the way to a big positive value of m. And I can evaluate that, which is a value in this. And if I had done that, and I had plotted all the evaluations of this for all the values of m, I would have gotten a parabola. And I would have felt a little silly, because I'm like, oh, I have a parabola. Maybe I don't have to do all that work, because all I'm looking for is where the parabola hits a minimum. And as we're going to see, that's going to turn out to be relatively easy to do. Now, one thing we should talk about is the parabola could look like that as well. So this is a U, and this is, let's call it an N, an inverted U. So what's the difference here? Well, let me remind you that the sign on the m squared term dictates the orientation of the parabola. So if a is positive, we have a U. And if a is negative, we have an inverted U. Well, if I'm computing the minimum, this is not what I want, right? Because that's the maximum, and the minimum is, well, I don't know. I really want this. Well, I'm guaranteed to have this. Why? Well, what is A? A is the sum of the square of the x terms. Every one of these terms must be, by definition, because I'm squaring it, positive, which means A must be positive, which means my parabola, my error surface that I'm trying to minimize over, must be a parabola, an upright parabola. So we don't have to worry about that right there. Okay, good. So that's that right there. A is greater than 0, A is less than 0. In fact, A is always going to be greater than 0. And so that's the minimum I'm looking for right there. Now, how do I find that minimum? Now, some of you may see where this is all going, and if you don't, that's okay. We're going to get there right now. So let me remind you now. I started off by computing the vertical distance between each data point and the model. I took the square of that, so I don't have to worry about the positive or negative, whether the point is above or below. And I'm going to minimize the error of all those to get a line that more or less goes through the data points while minimizing the deviation of each point from the line, a measure of goodness of fit. Okay? So I'm going to now just let me add a little bit of notation. I'm going to write this as an error function. So what do I mean by that? I'm saying E of m, a function of m, is just this. So if I put some value of m here, I can evaluate this expression and I get a number out. And if I put a different value of m there, I can evaluate this expression and I get a different value out. And if I enumerate all the values of m and I plot them out, I will get a nice parabola. Okay? And the reason I'm going to do this is because I now want to find the m that minimizes. And of course, we know that the m that minimizes is going to come from the calculus. Okay, so we'll get there in a minute. Now, let me remind you that when I wrote out this summation, I got a parabola. The a term is the sum of the square of the x terms. The b term is minus 2 times the sum of the product of the x and y terms. And c is the sum of the square of the y terms. Okay, that just came from writing out that expression. So now I have E of m is equal to a constant, known, we know it, m squared, plus b constant, known, times m, plus a constant c that, of course, is known. So now I have a parabola, there it is right there, and I want to know that value right there. So I gave a hint of this already, so how am I going to find that value? Well, this is the value where the derivative of that function, a parabola, is 0. Right? So if I take the derivative up here, it's the tangent at every point. So that has a negative tangent, and then a 0 tangent, and then a positive, 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 positive. So we have negative values here, positive values here, but right there, the derivative is 0. And where it's 0 is where the parabola hits a minimum, and where that parabola hits a minimum is my answer of what the value of m is. So now all we've got to do is differentiate a polynomial, and that's about the easiest thing to differentiate. So I take the derivative of this thing with respect to m, I'm going to set it to equal to 0, and I'm going to solve for m. So tell me where the derivative of this is 0. So let's remember how to do derivatives. For polynomials, this is pretty easy. So the derivative of am squared is 2, that's the power comes down, a, m, and then the power gets reduced by 1. So the derivative of am squared with respect to m is 2am. The derivative of bm with respect to m is 1 comes down, so that's just b times m to the power 0. So that's just b, and the derivative of a constant is 0. So the derivative of a parabola is 2am plus b. And what do I want to do now? Well, just set that equal to 0. So set 2am plus b equal to 0, and what do you do now? Solve for m. Well, we know how to solve for m. That's actually trivial. So m is equal to minus b over 2a, and there's your answer. So, by the way, what's b and a? We have to go all the way back to where we started. A is the sum of the squares of all the x terms. B is equal to the sum of the product of x's and y's. Compute those, multiply a by 2, take the ratio, negate it, and that is the m that minimizes this measure of goodness of fit. Okay? So, there it is again, just to remind you what the a's and b's, b's and c's are, is they come from the underlying data. You change the data, you get a different slope, of course. Okay? So let's see if this just makes sense. Like you look at this equation, and is there any intuition here, right? So we started with the model. We started with the measure of error, the vertical distance, quadratic error function. That's quadratics, it's squared there. And what did we do? We expanded this out. We got a parabola. We differentiated it. We set equal to 0, and we solved for m. And we got minus b over 2a. And that means it's the product of the x and y terms divided by the sum of the squares of x's. I don't have a lot of intuition for that. I mean, the math tells me it's right. It sort of looks right. But maybe it'd be nice to see if we can just get some intuition for this. Okay, so what if we just had a single point? Let's think about that. Well, first of all, let's agree that this model has 1 degree of freedom. And I only need 1 point to fit a line through that. Why, by the way? Because I'm forcing the intercept to be 0. And so take any point here, and the line that goes through that point has to also go through the origin, and so the origin is essentially the other point here to fit the line to. So with 1 point, I should be able to get an answer. Well, what does this look like for 1 point? Well, n is 1, so we can certainly evaluate this. There's nothing wrong with it, so let's look at it. Well, so m is equal to minus b over 2a. So that's just x1, y1 plus, oh, that's it. I only have 1 point. So it's x1, y1 over x1 squared. So it's x, y over x. Okay, so what is that? Well, it's just y over x. What's y over x? It's the slope of that point. That's exactly what the slope is. So I may not have a lot of intuition for that equation right there, but you can see that when I reduce it down to sort of this trivial case of n equals to 1, this is sort of doing the right thing. It's just telling me what is the slope of this. And that's sort of nice. There's a nice intuition behind that. Okay, so that is a form of least squares estimation. So least squares says that the measure of goodness of fit is the vertical distance between the point and your model. Whatever the model is, it can be a line, it can be a parabola, it can be anything you want. We're going to stick for lines for now. You sum up all those errors, all those vertical distances, and then you sum up all the square of all those points, and that's going to give you a parabola or a paraboloid in high dimensions. The paraboloid can be minimized by differentiating the error function and setting it equal to 0 and looking for the bottom of the bowl. That will give you the parameters that minimizes that error function. So the reason why we took the vertical distance, the reason why we squared it, and the reason why we took a simple sum is because it leads to that particularly nice formulation to solve for the minimum without some big gnarly brute force or nonlinear optimization. You simply compute a derivative, you set equal to 0, and you can solve analytically in one step and you get the answer. That's very nice. All right, in the next segment we're going to bring back the slope and we're going to throw away we're going to bring back the intercept and we're going to throw away the slope, and then we're going to put it all back together and show you how to do this with 2 parameters at the same time. All right, I'll see you in a few minutes.